Hello everyone, thank you for your interest in my presentation today. I am Dandina Rao, a professor in petroleum engineering at Louisiana State University. In the next 15 minutes or so, I would like to introduce to you a new combustion and heat transfer technology called HydroFlame and discuss its potential impact on oil and gas industry and some other industries as well. What is hydroflame? Hydroflame term stands for a flame that is always enclosed within a flowing stream of water. That means the high intensity flame is always surrounded by rotating water films. The key is to inject water tangentially so that water hugs the walls, leaving empty space in the middle along the axis, and insert a flame in the middle, as this video will show in a minute. Here is the plastic. We replaced the metallic combustion chamber with a plastic tube to demonstrate this concept, and this is a pilot unit that we built in Baton Rouge here. It's operating at low pressure, obviously, for 60 psi or so. That's just for demonstration purposes. And you see the water rotating and hugging the walls, and right in the middle is the flame. And that's how the name HydroFlame came about, to represent this fire in water concept. And what you see in this part of the video is the heat transfer section beneath the flame converts all that water, or most of the water, into steam, and so the steam and hot gas mixture, all at the same temperature, come out the outlet. We need some water purposely unevaporated to keep the dissolved salts dissolved in it. Well, this is a photograph of that pilot unit you just saw the video of, and here is the combustor, and these are the heat transfer sections. This is an evaporation section here, and the steam and gases come out of here at this point. The maximum diameter of the combustor is about 4.75 inches. We intentionally keep it under 5 inches, and the maximum length is about 4 feet. And here is just a picture of what you just saw the video of: plastic tube, combustor, and the flame burning in it without destroying the plastic tube because of the water films rotating around the flame. The progress we have made to date in developing this process and increasing its technology readiness level is shown here in this slide. The first one was the 340,000 BTUs an hour 5 psi hot water heater that you just saw the demonstration of. And then we built a 750,000 50 psi steam generator, steam plus flue gas, obviously. And then a million BTUs per hour operating at 100 psi, and a 5 million BTU unit operating at 750 psi. These are all steam plus flue gas, and the one was a 1 million BTU was a pilot lab tested scale, and the 5 million BTUs were skid mounted units which are highly mobile, and we have tested them in the oil field. These are ASME stamped and registered with the National Board. Fully automated operation with data acquisition systems. A continuous operation was tested for 48 hours without any human intervention. And like I said, one of the units has seen 2 field tests with positive production results. Well, this slide shows the dimensions of the 5 million BTU per hour field units, capable of operating up to the maximum design pressure is 750 psi, maximum operating pressure being about 600 to 650 psi. And the maximum diameter, again, like I mentioned before, is 5 inches. And the length of this 5 million BTU unit is about 8 feet in length. And this 5-inch diameter is intentionally capped so that it can be inserted into deep heavy oil reservoirs that have 7-inch casing. That's the idea here, is to deep heavy oil reservoirs. The steam is required where the oil is, and the intention of this design is to lower it downhole where the oil is and generate steam and gas mixture at that point and inject into the reservoir to heat the oil. Instead of surface generators and transporting steam and having to live with the enormous heat losses and inefficiencies. And the gases also are injected into the reservoir, thereby repressurizing the reservoir, increasing the heat thermal efficiency of the entire process, and also preventing heat losses to the overburden. Those are all described in other papers, and if anybody is interested, please contact me. I have my email address at the end, and I will be able to share that information with you. Oh, here are the pictures of the two 5 million BTU per hour 750 psi units that we have built mounted on trailers here, as you can see, to be able to move to the fields and from well to well in a field. This is the first unit, and the steam generator is right here. This is the second unit, and that's all. It has the steam generator here. It's about 7 feet long. I said 8 feet earlier. This is about 7 feet long. The steam generator itself is about 20 feet in length for the whole trailer, and there is a control room at the front. It's an air-conditioned control room that houses the computer that controls all the control valves and the entire operation of this unit, and also acquires all the data while running it. And I'll show some examples of the data in the next slide here. Well, before that, let's look at the way it was operated in a field nearby Baton Rouge. And here is the unit that's still not connected to the well bore. There is a well bore here, and it's disconnected because we wanted to test it. So we are operating it, and initially we operate it in such a way that all of the steam and flue gas mixture comes out the vent pipe until a stable operation is achieved. It takes about 10 to 15 minutes, and then the computer switches the flow from the vent to the horizontal pipe here, which is then connected to the well bore, and it goes into the well bore. So we wanted to test that operation, whether the computer correctly does the switch over or not, and that's what we are testing here, switch over, and that worked successfully. And then we disconnected this pipe and connected it to the well bore right here. This pipe connected to the well bore, which has a paper clip bend to account for the expansion due to steam going through that line. Well, this picture shows the connection to the well bore. Here is the well head here, and this pipe through a paper clip type bend to account for the expansion is connected to our device here. And a close-up view is shown here of that injection system. We are injecting steam and hot gases made from HydroFlame unit into the well at about 600 psi, shown on that pressure gauge over there. Here is a snapshot of the control panel in the control room that I showed a little bit earlier of this 5 million BTU unit. And this test was done on April 27, 2014. And as you can see, the unit was operating at about 5.16 million BTUs an hour and 500 psi. And the airflow, fuel flow, and water flow rates, pressures, and temperatures are all recorded here, and the steam temperature as well that's coming out of the system. Flame is on, and so on. And for emergencies, we have a stop switch as well. If you just hit that, it just shuts down the entire system. The actual field itself was a heavy oil field containing 16.8 degree API oil. That anything less than 20 API is considered heavy oil. It is about 1100 feet, and this field did not make any oil since 1985 or so, when it made about 5 barrels per day and declined to 2 barrels a day, and then it was shut in since then. And they attempted to produce in 2006, did not make any oil at all. And that's when we went into this in 2012 for the first test of the same well, and then again in 2014. And in 2012, we injected it for about a week, and then we soaked it for about 2 or 3 weeks, and then we produced it. Produced the same well. It's called a cyclic steam process. That's what mentioned here, and it produced about 1,200 barrels of oil in the first test, and then we went back again in 2014 and steamed the same well again for another 28 hours or so over about a week's period, and the well came back at, when put on production after soaking, at 14 barrels a day, and then totally in a few weeks it collected about 1,700 barrels. And the company reported to us that the test expenses were paid off within a few weeks of production. And that was the positive results of testing in the field that I referred to earlier. I would like to turn our attention to what's going on in terms of natural gas flaring around the world, and especially in Texas and the United States. There's a huge amount, millions of cubic feet a day. These are million cubic feet per day of natural gas flared and vented in the Permian Basin alone in West Texas. And in 2019, for first quarter, annualized value was about 661 million cubic feet per day. So much gas is being flared, and that has become a big concern because of the CO2 emissions and some of the unburned gas methane, which is even worse than carbon dioxide in terms of environmental damage. So there is a big concern of this, and what we are proposing to do is to use this flare gas as a fuel stream in our mobile units and generate steam and hot gases for injection into the wellbore. And that's what is shown here in this diagram. There is a production well here, and the production well, and the production coming out of this, of course, oil and water mostly. Crude oil is separated here through the separator and sent to the sales division. And then we pump the water, produced water, for a preliminary treatment process, preliminary only, not very detailed like the conventional steam boilers require. We don't require that kind of clean water. And then pump it into the HydroFlame unit here, generate steam and gases, take out the sludge that might come out of the produced water stream, and then inject the steam into another well. And that does the heating and production and so on. But excess steam can be used. It can be generated and used to run a turbine, which in turn, through shaft power, runs the compressors for fuel and air compression that are required to raise the streams to the pressure of operation of this unit. So it's a self-contained process of HydroFlame to increase the overall efficiency of our entire process, and the compression power required can also be generated by the steam that is generated here and the gases. And that's our future plans, to build something like this and test it in an oil field. The impact of HydroFlame technology on thermal enhanced oil recovery economics should be obvious by now. Because of the high thermal efficiency of this process, we can lower the amount of steam required to produce a barrel of oil, meaning very low operating expenses. Conventional technology requires about 3 to 5 barrels of steam per barrel of oil, and we have seen that using HydroFlame, because the hot gases are also going with the steam and repressurize the reservoir, the steam oil required to bring up a barrel of oil is about 1 barrel. 1 barrel of steam per barrel of oil versus 3 to 5 barrels of steam for 1 barrel of oil using the conventional boiler technology. It's a tremendous reduction in operating expenses. And like I said, the flue gas is going with the steam, stay in the reservoir. They rise to the top of the formation, stay inside the reservoir, thereby pressurizing the reservoir. Therefore, the pumping cost will be lower, and the production, the pressure and production last much longer. Production cycles last much longer, which is again beneficial. And when the gases rise and accumulate at the top, they also help prevent the heat losses to the overburden. That's a very important calculation in all this. And that's how the steam requirement over the years for producing heavy oils will be lowered, because you are filling up with an insulation layer of gas at the top of the formation. And also produced water recycle. As I said earlier, we could take dirtier water than conventional steam generators. And that helps a lot to lower the water preparation costs. And also the economic benefit of CO2 sequestration. This is bound to come around, and that benefit is also attached to the economics of thermal EOR by using HydroFlame process. And impact of HydroFlame on the environment is quite obvious. Mitigation of CO2 emissions, because all the combustion gases are also injected along with the steam into the formation, and that's a big benefit of this technology. Elimination of oil field flaring of natural gas that I just mentioned in the previous slide. And produced water recycle enables reduced freshwater usage. That's another environmental advantage. Plus, what the combustion process itself generates water vapor, and that as steam goes into the reservoir. So you need about 8 to 10% less water than conventional systems. And that's another environmental benefit as well. In order to conclude the talk, I appreciate your time. And HydroFlame, we have just introduced a novel concept of combustion and heat transfer, that is HydroFlame. We have proved it from bench scale, lab scale, to pilot, to field scale units. Extremely high heat transfer coefficients enable very compact steam generators so that we can place them downhole into deep heavy oil reservoirs, which is very expensive to produce all around the world. And we have a way to accomplish that. The flue gas from the combustion are also injected into the reservoir, thereby eliminating emissions altogether, like I mentioned. So 2/3 reduction in steam oil ratio decreases operating costs in heavy oil recovery projects. This has a tremendous impact on the economics of heavy oil production, and is ideally suited. HydroFlame is ideally suited for flue gas generation by burning flared natural gas. That I showed a little bit of that in this presentation. But we do have another presentation, paper 101, in this MIT 2020 conference. It's called the gas-assisted gravity drainage process, and I would appreciate if you can spend some time on that presentation as well. That talks a little more about generating flue gas and injecting in a specific manner called gas-assisted gravity drainage to produce light oil reservoirs. You don't need steam for light oils, but the gas itself is very beneficial. Gas injection EOR of light oils is quite common, and then this paper addresses that. Being a new concept, HydroFlame has several new applications: power generation, produced water treatment, oxy-combustion, produced water treatment, and coal gasification, in-situ coal gasification, and all that. So we have several applications to pursue, and several people to thank us for bringing this far in developing this technology. And their names are shown here, and a picture of the team some time ago is also here. And I'll be very happy to answer any questions you may have. Please address them to my email address here on the slide. Thank you so much. I appreciate your time.